So we're starting. We're starting with the Jamaica session, and the first talk is by Jacob Walcher, Jamaica Galaxy Mapping at Calar Alto. Are you ready, Jacob?
Yes, I'm ready. Let me share my screen.
Yes.
You can go ahead.
Okay, when you want to go ahead.
Okay, so is it visible on YouTube now?
Yes, well, we can follow you.
Okay. So good evening, everyone. This is a talk presenting the Galaxy Mapping at Calar Alto project, Jamaica. We have a consortium, and this talk would not have been possible without the contribution of many people at IAA, AIP, and the other consortium members, but I'll mention them somewhat later in my talk. I'll have an overview of that. Let me also say that this is a very personal moment for me. Calar Alto has been an important institution, actually 3 times in my career already. I did my very first, when I did my master thesis, I was contributing to the commissioning of Leica. I was a night observer at Calar Alto, and of course with the Khalifa project. So I really, really hope that this 4th time will be just as nice and successful as the first 3 times. What is Jamaica? The Spanish will not be surprised. It's a hammock looking at the sky. In somewhat more detail, it's an integral field unit of about 1 square arc minute with 2,400 fibers of relatively small diameter, 4 optical spectrographs, and we think it's a technically simple, affordable, and fast project that is optimized to map extended objects at high angular resolution. It's also a survey project to look at 2 of the 2 objects that can only be observed in the northern sky, which is the closest galaxy that is similar to the Milky Way, M31 or Andromeda, and I'll talk about this in this talk. And then the closest cluster of galaxies, the Virgo cluster, which Ruben will talk about in more detail. And we'll address some empirical questions, such as the properties of the ionized gas, the chemodynamical state of galaxies, and the interaction with the cluster medium. But we also have built into the project a group of theorists who will directly look at the connection to theory, such as feedback, interpretation through dedicated simulations, etc. So let me dive into the science context of the project. We look at galaxy evolution, and galaxy evolution is a complex process that is a process that has many sub-processes which run over the history of the universe. So from below to above, you have the usual representation of the history of the universe. And what we do here is we look at the end state of galaxy evolution, so galaxies in the local universe today. And we are interested in looking at their properties and using them to understand the processes and how they interact to make the galaxies we live in today, and in particular, of course, the Milky Way, that is our cosmic home. One of the fundamental observations in this context has been, over the last, say, 10 or 20 years, that there are 2 important mass functions. One of them is the halo mass function, which is the dashed line here, and the other one is the stellar mass function, and you can clearly see they have significantly different shape. There is in the middle a place of something like maximum efficiency. This is the knee in the stellar mass function, and that is actually where the Milky Way and M31 lie in terms of stellar mass. At lower masses, we think that supernova feedback is crucial for suppressing star formation, and at higher masses, we think that AGN feedback is crucial for suppressing star formation. But none of this has been really conclusively demonstrated because we do not fully understand the physics of feedback by supernovae or AGN. So in our quest to understand local galaxies, large surveys have been instrumental. They have been extremely important. Of course, the Sloan survey is a prime example, and this is the mass-metallicity relation that was derived from the Sloan survey early on. And as you can see, there is a specific shape to it, which tells us about the chemical evolution of galaxies, and it tells us about feedback as well, because we think that winds are critical in determining the shape of the mass-metallicity relation. When we did the Khalifa survey, we came up with a second version of this plot, essentially, And that version is now considered to be possibly the more important version because it's a local relation between surface mass density and the oxygen abundance in local galaxies. And here really it has been the spatial resolution afforded by integral field spectroscopy that has enabled this major step forward, which will help us explain why there is a mass metallicity relation in the first place. So if we look at it from this, from far above, what would be the next logical step? Well, the next logical step obviously would be even higher spatial resolution. So Sloan treated galaxies as a point. Khalifa, we have resolution of about 1 square kiloparsec. If we want to go to even higher spatial resolution at the mass of the Milky Way, there really is only one object in the sky, and it happens to be the northern sky, which is really available to us, and that is the galaxy M31. It's the closest galaxy with the same mass as the Milky Way, and it's therefore a prime target for essentially all observatories. Here I have just assembled images from Herschel, far infrared, XMM in X-rays, galaxy in the UV, and then optical. This is an NOAO image. And then also, for example, here just to show additionally the CO map from the radio astronomers. So the M31 galaxy is a galaxy that everyone loves, and it's the closest one and allows us the highest spatial resolution. So what is the spatial resolution that we actually want to target? This is a simulation by Philip Kirichidis, who is working at AIP and who's working on simulations of star formation. And what you see here is the surface density of ionized hydrogen. It's not exactly H-alpha flux, but it's somehow related to H-alpha flux. At least there is, how can I say that there is a continuous relation between the two. It's not linear. The resolution here is 30 parsec, and you can see that there are blobs and there are places where there's less ionized hydrogen. Now let's zoom into that simulation and look at higher spatial resolution. So this is 15 parsec. The difference is not that convincing. But now, as we go to a 4 parsec resolution, suddenly much more structure appears, and you can see that there are blobs of. Can you see my pointer?
No.
Okay, then I'll try to explain it. So there are these shells that are essentially the telltale signs of feedback around hot stars, and that is exactly what we're looking for. If you go to even higher resolution, then the change is very limited. There's very limited change because the natural scale of the ionized of the ISM structure in the ionized hydrogen is about 3 or 4 parsecs. So that is where the structure is that you want to look at. So that's what we're comparing here. And at the distance of M31, 3.9 parsec, which is here, is 1.3 arcseconds angular resolution, whereas 15 parsec is 5 arcsecond resolution. So you can clearly see that with the current PPAC IFU, we would be on the right-hand side, but with the proposed Gamaka IFU, or actually the PMAS lens array, we would be on the left-hand side. So it's crucial to go to a resolution that is essentially compatible with the scene. Also, the size of these patches simulated is about, this is 500 by 500 parsec, as you can see by the axes, but actually you want a bit larger because then you can have a bit more statistics on the structure. So if you think that you want to have 1 kiloparsec square patches and you want to have about 10 patches to look at the ISM in M31, then 5 radial ones, and maybe there are 5 special places you want to look at. And you consider the available time to observe M31, say over a period of 5 or 6 years, then you derive requirements for an instrument that is about a 1 arcsecond angular resolution and the 1 square arc minute field of view. So that was for the interstellar medium. Now let's look at what we can do in terms of stars. So, yes, just to say there is a design reference science case essentially that focuses on the H2 regions, and that will then be the subject of the talk by Genevieve Amicheva later on this morning. And that, just to collect the requirements, that says that we want to cover between 4,300 and 6,700 nanometers in the optical wavelength range. And actually O2 at 3,700 nanometers would be desirable, but for reasons that will be explained in the next 1 or 2 hours, this might or might not be possible. So now let's look at stars. This is to the right, you see an image of M31 with blue boxes that are from the FAT survey. That's an HST imaging survey of, as you see, about a third of the M31 disk. And to the left, you see one of the ACS images from FAT with an overlaid Gamakka footprint. Now, I have to say that footprint is an artist's impression. It doesn't have to be exactly what Gamakka would look like. Now, if you zoom into this, you see that this is 200 by 200 arc-second image. Now, if you zoom into this, and every white circle now is a fiber, then you see in many places, for example, if you concentrate on the upper right, there is a very bright star that is a single star for the fiber. So there's one bright star on average per fiber. There are fibers where there are more stars, there are fibers where there is no star, but on average, there's about one bright RGB red giant branch star per fiber. So essentially what you can do with these kind of data, you can actually take spectra of single stars in M31 without any pre-selection. That, of course, tells you right away that you want to look at something like a science case in which you look at the chemodynamics of the M31 disk. And also that science case, not entirely by chance, leads you to an angular resolution essentially compatible with the seeing, which is again 1 arc-second. So those two science cases together tell you that there is a fundamental difference between fibers of 3 arc-second diameter and 1 arc-second diameter. And that fundamental difference is important because it's the design philosophy of Gamakka. Of course, due to sensitivity issues, the RGB stars in M31 are between 19.5 and 22 in the visual. So with a 3.5 meter telescope, you don't get very high signal to noise. So in order to, what you can get is the velocity. You can just measure the velocity of a not so good spectrum. But in order to get other properties and really do chemodynamics of the M31 disk, you need to do other properties. I show an example here from the HST photometry, where Dorman et al. Have classified essentially the stars in the color magnet diagram, and they have been able thus to determine ages for these stars by just looking at where they are in the CMD. And of course, in the case of Gamakka, we would additionally use the spectra. We might use additionally K-band data. We might combine all of this into some machine learning algorithm, and that get higher precision for ages. We will probably also be able to get the metallicities. Whether we get the alpha abundances, I am not so sure, because really the spectra are not that good, but it would of course be desirable, and we'll study that during a potential phase. What can you do if you have this kind of data? Well, if you want to do chemodynamics, one of the fundamental observables is the age-velocity dispersion relation. So in this case, on the left, you can see what we know for the Milky Way, which is very detailed in that you see that there are dark blue stars. Those are the thick disk stars. They are different in their kinematics, and they are different in their stellar abundances. As you see, for example, you could separate a thick disk from a thin disk sample also in M31 if you choose the right overall metallicity and the right kind of kinematics. So with the data that we have, we think we can probably disentangle the thin and the thick disk within the areas that we would be observing. To the right, you see the famous age-velocity dispersion relation. The smaller dots below are for the Milky Way. The bigger squares are from the data by Dorman et al., where they have a sample of 7,000 stars with spectra from the Keck telescope. And you can see that there's a clear velocity dispersion to age relation, but it lies much higher, the velocity dispersion is much higher than in the Milky Way. Now, what we would really like to do to study what the disk looks like, what its chemodynamic status is of course to look at that into in different parts of the disk, where the bulge is, where the thin disk is, etc. Try to disentangle the different components. And in order to do that, you want a factor of 10 improvement so that you can subdivide in different areas. And that again leads you to a sample of about 200,000 stars. It leads you to a field of view of about 1 square arc minute. And it sets another fundamental requirement, which is that you want a instrumental dispersion of about 80 kilometers per second, such that you can actually do the velocities. You can also do velocities with really low signal to noise, even for 20-second magnitude at signal to noise 1 in 1 hour, which is what we could get with Gamakka. We can still do velocities. We'll do much better velocities for brighter stars. We'll maybe do more with brighter stars, but that is like the lower limit where we think we can actually get some impression of the velocities of the stars. And you can see here that even if the signal noise is limiting our precision, given the current shape that we think is applicable to M31, where you have the velocity dispersion of, say, upwards of 40 kilometers per second, we think we can still look at that dispersion, edge dispersion relation with the data we would get. The example number 2 is again taken from the Milky Way. This is a paper from the RAVE survey where they have analyzed the velocities of a sample of 73,000 stars over 9 square kiloparsec. And they have seen that the disk of the Milky Way wobbles. So you can see the different colors are different vertical velocities, which would be what we would be getting from Gamakka, because M31 is, well, not nearly face on, but it's quite face on. And so we would actually be able to see these kind of wobbles as well in the M31 disk. And for the Milky Way, there has been, the simulations have been run and interpretation is ongoing as to exactly what these wobbles mean. In the case of M31, I would actually expect stronger wobbles because there is a clear, there's a clear distortion to the M31 disk, which should also translate into the kinematics. So the derived requirement is the same as before. And then something that I'm not sure we could do, but I would like to put up nonetheless because it's interesting, I think if we could do it, is looking at streams inside the disk. So in this case, I am showing a paper by Meingast et al., where they have looked at the velocity substructure in the Milky Way disk. Now they have, of course, 3-dimensional velocities. In the case of M31, we would only have 1-dimensional velocities. But if you look at the left-hand plot and you look at the somewhat more prominent black dot on the left-hand side, that is the Hyades cluster, which is offset by 30 seconds from the normal rotation velocity of the Milky Way. So if there are similar groups of stars in M31, then we will be able to find them just by a single velocity difference to the overall disk. The sample analyzed here is about 700,000 stars within a 600 square parsec box. So as I say, in terms of statistics and precision, that is limit of to what Gamakka could do. But on the other hand, we'll have a much larger area, so maybe we'll have more chance of finding more prominent streams. So looking at the area, this is the area that is covered by the Milky Way with Gaia. And what you see for the different, you see an artist's impression of M31, and then you'd see different colors. The colors represent the different depths of the data. And what you see is that the coverage and the footprint and the detection functions are really, really complicated for Gaia because we're in the middle of the disk. There's strong absorption in the Milky Way disk. And so depending on where you look, depending on many things, your depth will be different. For the survey they're proposing for M31, it's completely different. We can choose the footprint. We look from above. There is little extinction, or it is well known from the ISM studies. And for example, one way of doing this is a rough sketch of what the Gamakka area could look like if you decide to go for a single radial strip. That would actually get you 200,000 RGB stars over an area of 12 square kiloparsec. You could also, of course, do the footprint in a completely different way. You could, for example, choose to put 10 different fields in different places. Again, radially, maybe then going further out, along the major axis, along the minor axis. For Gamakka, you have the freedom of choice to do this. And of course, it would be a matter of a phase A study and even a later optimization to determine exactly what the optimal footprint would be. Jorge, can you tell me how I'm doing in terms of time?
Actually, 2-3 minutes, Jacob. Jacob.
Okay.
2-3 minutes. Sorry.
Oh, really? Oh, wow. Okay, then I need to speed up really. So Ruben will talk about the Virgo cluster. This is our table of top-level requirements. I have mentioned them already, so this is here for overview, but I'll just jump over them. This is typical data that we would get for Gamakka from the MUSE data from NGC 300. Now, MUSE sits in the southern sky, so we cannot use MUSE on M31. But you can see, particularly, for example, if you look at the emission line structure, then you can clearly see that there are exactly those structures that you saw before in the simulation by Philip. Now, what I wanted to highlight, one thing that might lead, that you might doubt is, can we extract the spectra of single stars from the Gamakka data? And the answer is yes, we can. There is a postdoc, Sebastian Kammann, who has developed a software called Pampelmuse, and you see how it works in the lower panels. To the left, you see an HST image. In the middle, you see an image from PMAS at Alto, which was used to develop that software. And to the right, you see the extracted spectra of the deblended stars. And you can see that we can clearly do extraction of stellar spectra from such data. GAMACA would be very visible publicly because we would provide data to the public in data releases. In the interest of time, I have to jump over this. I apologize. I would like to point out this slide where you see in light blue the area that is incompatible with our top-level requirements, and in black you see all of the competing current IFUs that are available. In blue are availables that are in the southern sky. So what you see here is that the only IFU that would be compatible with our top-level requirements is MUSE, but it is in the southern sky. So GAMACA will be the only instrument in the northern sky hemisphere capable of doing the science we're proposing with those two unique objects, M31 and the Virgo cluster. Talking a bit about the instrument management and development path, we have a two-tier participation. So we have first the consortium. These are the institutes that would commit to invest money and resources, and they would be the one to decide on the science and the service strategy. But because M31 is such a well-known target, there are many people in the community who have a lot of knowledge that they could bring in, and therefore we have devised a science team which can bring in specific science know-how and participate in the exploitation. The two co-PIs are Ruben, who will talk after me, and myself. Other roles, for example, the project scientist would be assigned during phase A. The timeline is about 3 years, and Andreas will present the timeline later, so I will not talk about this. But something that I would like to highlight here is that the total cost of the instrument currently is about 2.5 million euros for the baseline that is compatible with the top-level requirements, of which approximately 1 million is already available as hardware, as in-kind contributions from AIP in our lab. So we just need to raise 1.5 million euros, and the 1 million euro is essentially existing spectrographs for which there is no risk in terms of design, manufacture, etc., etc. Also, GAMACA is designed to be modular and scalable, which means that if we get additional funding, we could probably increase the field of view or potentially the wavelength coverage. This is, as I said, a long list of people who have shown interest, are associated and have contributed to the current presentation and the proposal that we wrote, led by IAA and AIP, and then University of Granada is member, and UNAM, and then we have the science team with different people from representing different expertise, such as past M31 surveys, or as I just mentioned, specific software packages. The risks, I'll just quickly go through that. We need to set up project management and systems engineering, which we haven't done yet. And that is, of course, a big risk, and we need to do that before we can start phase A. So that's something we will do over the next week, also based on feedback from Alto, I guess. The second one is that I really worry about the insufficient sensitivity for chemodynamics. So here we really need to optimize so that the signal to noise 1 that I mentioned before doesn't bite us in the end. There is a technical risk in terms of a free-hanging fiber chain that we need to hang off the Cassegrain focus of the 3.5 meter telescope, but there is experience due to the Carmenes fiber, so we think that's probably manageable. And then there is sky subtraction, which is of course critical for extended objects, but here again we think that's not too hard to do with either offset skies, use of MalecFit, or other early benchmarking of strategies. Okay, this is my summary slide. I'll just leave it up and finish here. Thank you very much for your attention.
Thank you, Jacob. I think there was a question. Can you please go ahead?
Yes, can you hear me?
Yes.
Yes.
Okay. Hi, Jacob. Thank you very much for your talk. I have just one question. Given that for all the chemodynamics analysis you need, or in principle, you would like to have all. Is not a bit too inclined M31 for getting the vertical and the tangential velocity separated so you can do that analysis?
No, that's actually an advantage here in this case. It's not generally an advantage, but this case is actually an advantage because when you go, if you do one cut along the major and one cut along the minor axis, you get the entire ellipsoid. If we're seeing M31 face on, you will only get the vertical component. But because you see it at 30 degrees, you would actually see the velocity ellipsoid.
But in principle, if I remember correctly, the paper by Merrifield and collaborators, I don't remember he was actually the first author, but I think it was something between 45 degrees was the optimal inclination. So that's why actually, for example, for Megara, we went for M33 because it has an inclination that is more optimal in that regard. So in principle, you think that for M31, it will be also feasible?
Absolutely, I think it would be feasible, yeah.
Okay.
I think it actually, M31 is better. The thing that I know is the disk mass survey, where they have actually chosen nearly face-on galaxies, and they regretted that choice afterwards because if they had chosen a bit more inclined galaxies, it would have been easier to get the velocity ellipsoid in disk mass survey.
Okay, thanks.
Thank you.
Okay. If there are more questions, otherwise we move on to the next talk, which is by Rubén García Benito. Rubén, are you ready?
Yes, can you hear me?
Yes, sure.
Okay. I'm going to start sharing the screen. Okay. Can you see my screen now?
Yes, perfectly.
Fully, okay. So thank you very much. Thank you, Jago, for the nice previous talk. So I'm going to present the Virgo cluster in Jamaica. As explained by Jacob, we are a full consortium with different institutions, with a lot of people, plus a very sound science team from different countries, from UK, from France, from Russia, from China. So we have a solid expertise within the collaboration. I will try to show within the talk. So as explained by Jacob, M31 is one of the best targets for very precise spatial resolution. And if we go to the next order of magnitude in spatial resolution, we can go to the Virgo cluster. We are now probing here a spatial scale of 70 parsecs per arc-second. And why Virgo? Well, this is a 3D cosmography. So here we are mapping 8,000 galaxies colored according to their relative motions. And we know a great deal of things about our neighborhood in the local universe. And with Virgo, we have plenty of data to play with and to make a solid statement about the physical processes of the galaxies. We know that H1 stripping is responsible for galaxies migrating from the blue cloud to the red sequence in different environments. And here we have different stages where the galaxies may go through. And Virgo is one of the best, the closest northern hemisphere cluster and one of the best cases to study all these processes. And for that, we have chosen the VIVA sample, the VLA imaging of Virgo galaxies in atomic gas. They cover all morphological types, the spirals, especially well distributed, covering the main filamentary structures of the clusters, with a very nice H1 resolution. The good thing about Virgo, as I said, is we had a great knowledge about different properties. And we have a very solid ancillary data from H1 with the VIVA sample, which is one of the best in the spatial resolution with 15 arcseconds. All the bands in the infrared by Spitzer. In optical, we have plenty of them with a superb spatial resolution by the next generation Virgo cluster survey, with ultraviolet, and even in X-ray with ROSAT, and then the future survey with the Russian-German Eurosita survey. This sample is, as I said, is homogeneously distributed. In morphology, this is 43 galaxies. And we want to make very detailed studies with very good spatial resolution, with very good spectral resolution. Okay? These are the phases. You will see some of them along the talk with different morphologies and different environment studies. Also, they cover different projective sizes they peak in this is the B25 major axis in the optical V band, okay, and they peak more or less in 4 arc minutes in the major axis. So we will need different mosaics for them. And here you see different morphologies, H1 morphologies. In the top row, you can see examples of gas-rich galaxies in gas-rich environments in the outskirts. The middle shows galaxies at intermediate distances from the center of the galaxy, while the bottom row shows examples of several truncated H1 disks. Okay, and you see there the size of some of the examples with the 1 minute arc minute rule. As I said, we have a great deal of ancillary data to play with and to make solid statements about the different processes. So besides RAM pressure, this intracluster medium can affect the interstellar medium within the cluster of the galaxies. So there is another process that can affect, for example, the magnetic draping, which is the formation of magnetic pileup region and magnetic tail. As I said, here, this paper made a very nice presentation of these effects. And the point to take is we have very good data to play with what is lacking is a very coverage of full 3D spectroscopy of a good sample of the galaxies. Even we have this X-ray emitting from the Chandra, and you see that they're suggesting that the turbulence may be preventing the hot gas there from cooling. Okay, so from now on, I'm going to present some of the science cases that we can do with this sample. So we have radio continuum observations for some of the galaxies, and they can help studying the effects of RAM pressure. The polarized radio emission of a galaxy is enhanced on the side that faces the action of the RAM pressure, in which case the magnetic field gets compressed and show a higher degree of polarization. So the combination with the optical 3D spectroscopy from the stellar and gas kinematics is crucial to characterize these properties of the shocks created by the interaction between outflows events in the ISM RAM pressure. And here the spatial resolution and the spectral resolution are crucial. Also, the very famous are the so-called jellyfish galaxies, which represent extreme cases of gas stripping by RAM pressure. For studying these objects, multi-wavelength analysis has been proven to be very powerful. And here again, scales down below the 100 paxes are needed for these studies. There you see a bridge between one of the galaxies of the cluster with other two, and with each H1 bridge, and all this stripping from the galaxy. So the analysis of chemical abundances, the kinematics, the star formation densities will be crucial to understand these galaxies. Also important are the kinematics, and this is superb because of the spectral resolution provided by Jamaica. To the right, you see an example of the kinematics, stellar kinematics, of the same level of accuracy we can do with Jamaica. And important to the left, we have the famous lambda over ellipticity plane. And the important here thing are the shadow ray regions and the dots. These are simulations. And within Jamaica, we have a full set of expertise of theoreticians and simulations that we can compare all these analyses. So another importance is we have selection from the H1 sample, from the EVA sample, is the H1. As you know, H1 is typically not regarded as intimately related to star formation in galaxy. However, in this plot you see that Wang et al. Recently demonstrated that if only the H1 gas that is within the stellar disk of a galaxy is considered, then the average H1 surface density is extremely well correlated with a galaxy position above or below the star formation main sequence. So combining the H1 with the star formation rates, the star formation histories that Jamaica will measure, it will be possible to determine at what stage the RAM pressure stripping of H1 gas impedes star formation. And if the Wang et al. Results hold for the cluster environments, then star formation will not begin to shut down until H1 is being stripped from within the stellar disks. We have also a number of very interesting objects. Here you see NGC 4772 that shows a faint outer disk light and a very thin and well-defined inner ring. So this galaxy seems to be a past minor merger candidate with a bright, largely spherical bulge in the center and an odd, narrow ring with a strong near-side extinction. And also in the outer parts, there is a non-coplanar broad pseudo-ring, only visible in each one, that is kinematically decoupled from the first one. So the kinematics and stellar kinematics here will provide a full consistent picture of this and other interesting objects. And again, we have outflows. So with the superb spatial and spectral resolution for Gamakka, we will map the spatial and velocity distribution of the gas in outflows, as well as to identify possible gas clumps at scales of 70 parsecs, which is crucial for this kind of analysis, along the extension of the outflow. And this will allow to discriminate between shell and clumpy outflows models for calculating the feedback effects. Also will give us access to the optical diagnostics for testing both negative and positive feedback effects and identify flow ionized gas against possible effects of ram pressure that you see in here. All these available things that we will have in Gamakka. And here's a statement about the spatial resolution. This is an example of one galaxy and the full scale in SS long. And then this is what we would see, we will observe with Khalifa or Manga due to the PSF. The logo Khalifa is the full field of view presented there. And this is what we will see with Gamakka. You see that we can prove better spatial resolution. And in assuming here, you see in the ring, in the orange ring, you see that in Gamakka we see there like 3 H2 regions, while in Khalifa or Manga with the spatial resolution with the PSF, we cannot resolve these spatial structures. So also for the blobs in the outflows, for the studies in H2 regions, it will be very important. This is an example of the abundances, oxygen abundances variations azimuthally done with MUSE. Okay, and we could do in Virgo this very similar spatial resolution for metallicity variations with the Gamakka. Mind that in MUSE they don't have the auroral line, the oxygen-free auroral line. So with Gamakka we will have it, and we could do azimuthal gas properties very precise with metallicity, study the ionization parameter and the effective temperature. And finally, we can also do a kind of chemodynamics. So one of the important things is study the radial variations of the alpha over iron in galaxy disks. Thanks to that, we have a very good spatial resolution and covering all the full optical image of the galaxies. This is an example. This is a simulation for the Milky Way, but it's showing that we can prove a different radial steps of the galaxy, the variations of the alpha over iron and the metallicity. And also, we could do the variation in the mid-plane, towards the mid-plane, so the high. And here you have different samples of the Viva sample that we could do. And to the left, you have an example from a simulation, but this is the kind of thing we can do with Gamakka. Also, we can prove the thick disk. For example, there are models that they try to say that the rapid L formation of the thick disk gives a rapid decrease of alpha over iron. And to the right, you have an image of different models, star formation models. For example, look at the orange one, that if you see down there in the alpha over iron evolution, you will see that they show the different star formation models, so very different alpha over iron behavior. So this we can do this kind of analysis also with Gamakka. And finally, also we can study the Imf variations thanks to the superb spectral resolution. This is an example by Martin Navarro using a spectral resolution of 3000. And here with the TO lines and other features, we can disentangle the effects on the line strengths of these lines, the effects of the IMF or the magnesium over iron. And this could be done also with Gamakka. This is another example with La Barbera, and you see the variation of these lines across the different distances from the center of the galaxy. And again, thanks to the spectral resolution and the spatial resolution, we can do this kind of analysis. So all the top level requirements are achieved by the instrument for these studies in the Virgo galaxy. And I will finish with just the observations. So M31 and the Virgo cluster are very close in the sky. So they can go one to the another when they share the nights and they don't collapse. So we can go from one observation, M31, to the Virgo cluster in the night that they converge. And this is a simulation of the number of mosaics or the points that we will need for different types of galaxies. So this will be the largest optical IFU legacy survey on individual galaxies for area coverage. We will have plenty of data for individual. Again, this is like an M31, a precision detailed analysis for the galaxy. Just to show that we have the expertise for very big mosaics in IFU data. This is an example of a project with Nanjing University, mapping just the center of H alpha, combining 23 points, okay? So that's it. Thank you very much for listening.
Okay, thank you, Ruben. Is there any question for Ruben? Well, in fact, I have a question, Ruben. Can you go back to the slide where you showed the exposure times, just because you went very quickly through it? Ruben, can you hear me? Can anyone hear me?
Is your microphone on?
It's on, yeah. So, can you hear me?
Yes.
So, okay. So, can you go back to the slide where you showed the exposure times? I think it's 4 slides before the last one, the table, because.
Yeah, sorry.
No, so this is your screen, I guess. Okay. Please, can. Okay, so it's 1 hour per galaxy, and point. Okay.
Yes.
And
Yes.
you go slides forward now, where you show the number of pointings is.
Oh, yes.
It's this one. So the last one, the one which requires 80 something, is all a Virgo galaxy, or is?
Yes. All of them are Virgo galaxies. Yes.
Okay. And which one is? Just curiosity.
I have to look at that. I don't remember the name now, but yes.
No, okay. It's okay.
Yeah.
Yeah, but most of them is between 8 and 15, something like this. Okay.
Yes.
Okay. That was my question. Thank you very much.
Now that you are talking about this plot,
Yes, of course, yes.
this is Armando. Just one quick question. Is including the dither to cover the 100% field of view?
Yes.
Or is just,
Yes.
or you're not going to do that?
Yes. We're, well, at least at this stage, we're going to do that. But in phase A, we will set all this up. But this is including that, yes.
Okay, thank you.
Okay, thank you very much, Ruben. if there are no more questions, we move on to the next talk. Genoveva Micheva, are you there, Genoveva?
Yes. I'm in Martin's office.
Okay. Can you please share your screen and so that you can start?
Cannot open.
Oh yeah, Ruben, please. No. Okay, now it's okay. Thank you, Ruben.
Sorry for that.
No, it's okay. Okay, Genoveva, thank you. We are seeing your screen, so when you want, you can start.
Yes. Let's make it full screen.
Yeah.
Why is it in German?
So it should be. No, there we go. Okay.
Okay. So now you can see the screen, correct?
Yes, we see the screen.
All right.
Okay.
Let me start my timer. Okay, so I'm going to present the science case for the ISM in Jamaica. As Jakob already mentioned, M31 is very well studied, but there are two examples that I really need to mention here, and that's the paper from Azimlu 2011, who present a catalog of almost 3,700 H2 regions. It's on a telescope that is of comparable size to the 3.1 meter at Calar Alto. And this is a very large catalog of H2 regions, but the only properties that they provide is the size of the H2 region based on the H-alpha distribution and, of course, H-alpha line measurements. Another important survey is the FAT survey. Jakob already mentioned that one. That's a catalog of 2,700 clusters. Many of them, or the majority of them, are young, so they would have also an H2 region. But what they provide is broadband photometry and, of course, SED fitting. So from that, they can get age, and they do some surface brightness profiles. So they have effective radii and so on. So what we can, here I want to show you what this looks like. So this is the Azimlu study. So on the left, you see all points are the H2 region. So they're distributed all over the M31 disk. And the colors are just different luminosities. On the right, you see that their study improves on the decomposition of individual H2 regions into smaller clumps. So what we want to do is then make a catalog of approximately 1,600 H2 regions that will be detected in our footprint. And the reason why this will be a competitive study is because we can provide all of the emission lines within our wavelength range. So for every H2 region, we'll have these emission lines and emission line ratios. Some of them are very important, right? So you have sulfur 2, for example, you can obtain electron density for each H2 region. Then you have the oxygen 3, you can obtain electron temperature. And because you also have H-alpha, H-beta, you of course have an extinction map. Because we have the temperature, you can have the speed of sound, this CS there. And then also the Mach number. The Mach number tells you how much faster than the speed of sound your gas is moving. And of course, also we'll have velocity and velocity dispersion.
Can you hold on? Andreas tells me that on his screen, your slides don't appear. Can we ask?
Yes, in mine as well.
We are seeing just the first slide. Is it what you expected? Sorry.
No. Oh, I have actually moved on quite a bit.
Does any change here?
Now it changed. Now we are in the fourth one.
Okay, so people have not seen the previous slides.
Well, okay, I would just go back just a tiny bit.
Okay, so you could, yeah.
Let's see. Well, so basically I showed this here, right? So the Azimlu study with very many H2 regions, but they only provide H-alpha and the size. And then the FAT survey, which provides broadband photometry. This is what the Azimlu study looks like, right? So all of these dots here are the H2 regions. And here you can see that they have actually decomposed the individual blobs into sub-regions. So they improve on previous studies. And do you now see my slides?
Yes, we can see the slides.
Okay. So, and what we're going to do is we're going to provide all of these lines here in our wavelength range. And as I said, we can get electron density, electron temperature, the extinction. speed of sound, Mach number, etc. And because we can also then do SED fitting to the ionizing sources of the H2 regions, we can also obtain parameters from that, such as the mass, ionization parameter, age. Then there's also the dust fraction inside of the H2 region, the ionization fraction, etc. So this will be the largest sample of its kind, and you can do very many things because it's a statistically large sample of H2 regions, and it will be fully characterized with all of these properties that we can provide. You can do very many things with that. So for example, you can do a temperature study in M31 and then compare it to the Milky Way. So for the Milky Way, this was done by Bolser 2018, who then detect that the electron temperature behaves as a function of the galactocentric distance of the ionizing source. So what we can then answer, the questions that we can answer is, does the same apply for the M31? Is the slope different perhaps? Or does a linear relationship apply on all scales, right? Because we can go to smaller scales. I would then just move on. So this is then the example from the Milky Way. This is what it looks like. So all these dots are the H2 regions, and the color is the temperature. So you see where it's dark color, it's lower temperature, and then brighter color is higher temperature. And here you see for their two samples on the right, you see that for any azimuthal range, they basically obtain the same relation. So we can do the exact same thing in M31 and see if there are any differences. Another thing you can do is an excitation study. There are different ways you can do that. But for example, with ionization parameter mapping, that helps you detect optically thin or optically thick regions because it traces the morphological structure of the gas. It was first applied by Pellegrini to the Magellanic Clouds, and it has since then successfully been applied to, for example, these galaxies that I list here. And in all of those, ionization parameter mapping shows that there is an outflow, that an ionized outflow which reaches the outskirts of the galaxy, and therefore possibly Lyman continuum photons can escape into the circumgalactic medium and beyond. And then I want to mention that these two galaxies in blue, HARO 11 and Tulol 1247, are actually confirmed Lyman continuum emitters, and therefore this means that IPM actually works as an indicator of Lyman continuum escape. So this is what IPM looks like in these example galaxies. The red lines in the right image show the ionized cone that they find. And if you look up there where it says sulfur 3 over sulfur 2, you see that sulfur 3 is very, very strong, even in the outskirts, right? Or in the center, but it goes all the way to the outskirts. While if you look at sulfur 2 over H alpha, you see that sulfur 2 is very strong on the other side of the galaxy, meaning that that's an optically thick region. And consequently, this implies that Lyman continuum escape is not isotropic. Then another example is Tulol 1247. So you can see it on the right-hand side. You see that there is a, oops, sorry, something happened. Okay, do you see my slides again?
Yes, number 10.
Okay. All right. So, well, basically now we do it in oxygen 3 over O2. So if you look at the upper left corner, you see that it's very, very strong, not just in the center, but also all the way out to the outskirts in both directions, implying escape. And indeed, this is a confirmed Lyman continuum emitter. So other than that, you can, of course, use helium-2 as an excitation tracer because it's very high ionization, and this will trace Wolf-Rayet stars. And also, of course, the electron temperature itself is a tracer of excitation. But what you can then do is try to estimate the escape fraction of Lyman continuum. So on the right, you see SED fits to individual clusters, and on the left, you see to the entire galaxy. This is for Tulol 1247. And here you also we have taken infrared data and radio data in the FIT, and M31 also has that. So that will be doable. I want to then mention the case of the kinematics. So of course you can do a velocity field and velocity dispersion and study those, but I want to mention specifically this diagnostic, the intensity versus velocity dispersion. So on the left, you see basically temporal stamps or time stamps of different evolution stages of H2 regions and how that affects the I sigma diagnostic. And on the right, you see an actual real life case from Moiseev and Luzinskaya. Moiseev is a member of our consortium. And you can see that basically these central regions where the velocity dispersion increases, those really pop out in terms of these elongated filaments or fingers. So then you can match that to simulations and build a temporal distribution of H2 regions across the disk. Then I want to mention the size-density relation. So there is a relation between the diameter of the H2 regions and the electron density. In the Milky Way, this has been done by many people. I just show some examples here, but you see for every single, so the x-axis is always the diameter, the y-axis is always the density. So you see that basically it's the same relation. This has also been done for extragalactic H2 regions. So here in the left-hand side, you see 1Zwicky 18 in red. So it's those red triangles. And in the right-hand side, you see the antennae galaxy. So that's the open diamonds. And you see that they are offset. I mean, they do have the same relation, right? It's the same slope, but they seem to be offset from galactic H2 regions. So what we can do is test if the same applies for the M31, for the H2 regions in M31. And because if it does, then we can say, well, okay, so then mass of the galaxy is not the driving factor for this offset. And if there is an offset, then we can exclude a redshift evolution of this offset. So finally, I want to mention the feedback of the ISM. This is of interest, especially for the theorists in our consortium. So basically, they want to look at galactic winds and the outflow of gas from the galaxy. And why is this important? So first of all, when you have an outflow, if the outflow continues and expels the gas, if it's not slowed down, then you will quench the star formation in the galaxy permanently. But if it slows down and comes back in the form of a galactic fountain, then the quenching may be temporary. But the important thing is like what drives this, right? Is it supernova winds? Do you need radiation? Do you need magnetic fields? Or can you do it with cosmic rays? And I specifically want to mention cosmic ray driven outflows because it's a very new hot topic, or so the cosmologists tell me. This is a slide that I took from Christoph Frommer, who is also a member of our consortium. So here on the right-hand side, you can see an edge-on disk, right? And you can see these two biconal structures. So that's a biconal outflow. And this is driven just by cosmic rays. Now, how does that happen? Well, cosmic rays don't interact with the gas because the cross-section for interaction is too small because they're too energetic, right? They're relativistic particles. But they are charged particles, so they interact with the magnetic field. And they can, once they're injected in the disk, they create a pressure over density. So they push the magnetic field lines away. They push them away from the disk. And because the magnetic field lines are parallel to the disk, they're basically pushed in a perpendicular direction away from the disk. And because the magnetic field lines then couple with the ionized gas via the Lorentz force, they drag the ionized gas with them. This takes a long time. It takes 100 to 150 million years to build up. But once it gets going, it's basically unstoppable because the gas continuously gets an energy insertion, right? Well, if you compare this to supernovae, the gas is just initially very high, very quickly accelerated, but then the support stops. So then it can cool adiabatically, radiatively, and then it can come back. But with cosmic rays, it cannot. So what the theorists want to do is they want to use our observations to calibrate their simulations. And the observables that they will get is basically temperature and the distribution of gas. And they have all of these components: supernova winds, radiation, magnetic fields, cosmic rays. And they want to basically reverse engineer reality by comparing our observations to a combination of their simulations. So what can they tweak? They can simply turn things on and off, right? So they can turn off supernova winds, radiation, cosmic rays, or they can combine them, have some kind of a combination, like a fraction of every component, etc. And they say that they can only do this on M31 because it's the only galaxy of Milky Way mass that provides a sufficiently detailed view and a sufficiently close. So only with Gamakka, they say they can do this. I think here is the last slide I want to show you. So this is from Philip Girihidis, also a member of our consortium. On the left, you can see an edge-on disk with no cosmic rays. So cosmic rays have been turned off. The feedback has been turned off. But on the right, you can see what happens if you include cosmic rays. And you see that you have gas at the much further distance from the disk if you have cosmic ray feedback, right? So all this dark yellowish stuff is ionized gas. So basically, that is all I had. Thank you very much.
Okay. Thank you, Genoveva, for your nice presentation. But is there any question for her? Okay, so if there are no questions, we move on to the next talk by Andreas Kelz. Are you there, Andreas?
Buenos everyone.
Buenos días. Good morning.
How's the connection?
We can see you.
I was very much looking forward to see you all in person in Granada. It's really a pity that this is not possible this time. So hopefully this will happen soon. And as I always very much enjoyed my time for the last 20 years being either at Calar or at Granada. What I do now is I will share my screen and hopefully this does work. So basically now you would have to turn.
Yes, we can see your screen now.
Excellent. So it does not work, please tell me.
Sure.
For the people who do not know me, my name is Andreas Kelz. I'm heading the 3D and multi-object spectroscopy session at AIP, and in the past and now I'm involved in various instrumentation developments, DMAS, Virus for Hubble-Eberle, Muse for the VLT, and now foremost for the ESO Vista telescope. And after you now heard 3 exciting science talks about Gamakka, my task is to show you how we want to make this actually work. So my talk is about the Gamakka instrumentation concept and basically concentrating on the work packages, on the Gamakka subsystems, and I will also tell you something about cost estimates, technical readiness reviews, project planning. So, Jakob already said something about the top-level requirements, and Ruben as well, which obviously are derived from the science cases. That is all nicely outlined in the proposal. So you saw those numbers about the wavelength range and the field of view and the spatial sampling that we want to achieve. How is that going to happen? So this here is a sketch of the space envelope of the Gamakka instrumentation. So essentially what we propose is to have a set of modular spectrographs which are located, if possible, as close as possible to the telescope, so somewhere at the 3.5 meter dome floor. Obviously, all these things need to be discussed and agreed upon with the relevant Calar staff and in terms of safety requirements and whatever is involved in these kind of things. And then these modular spectrographs will be connected with optical fibers to the existing Carmenes front end. And inside that front end, we foresee the 4 optics that we need and the IFU head. So it's a rather slim design in terms of space envelope and infrastructure that is needed here. How does it look in terms of work package breakdown? I have not shown any science or organization stuff, but concentrated on the technical work packages. So obviously on top there's project management and quality assurance. Then we have system engineering and the system assembly, integration, test, and verification of being, global things. In blue, you see 5 technical work packages, which is the front end and the fore optics, the IFU and fiber system, the spectrographs, the detector and cryo system, and electronics and control. Calibration at the moment, and I will say more about it later, we rather see as a concept than as being a hardware unit. And obviously we have data reduction pipeline and we have the interface to the operation at Calar Alto. So let's go through the technical work packages and subsystems. So we foresee that the Gamma-K front-end interface is all accommodated in the existing Carmenes front-end. Obviously, that needs to be verified in the feasibility study. So we foresee a second pickup mirror or element for Gamma-K. There will be a fore optics. Most simple case would be focal reducer lens. We do not foresee any atmospheric dispersion correction. In fact, the correction will be done in the data cube, and that is a procedure we have inherited and have good experience with from the Muse pipeline, where we work with fixed tables. On the side, there should be a technical camera for acquisition and guiding, and then basically the light from the fore optics is directed to the integral field unit head. So this concept would actually allow that we still have the option to quickly switch over between Carmenes, PMAS, and then Gamma-K. So that shall, in terms of operation, make no difference to the current situation. In terms of the Gamma-K IFU, so if we, as a baseline, think about a monolithic IFU, the rough parameters are a field of view of the arc minute on the side with roughly 2,400 spexels or spatial elements, and a sampling, as Jakob said, between 1 to 1.2 arc seconds, not larger than that. How that will look in detail if we have a lens array or a bare fiber IFU, if the spexel size is round or hexagonal or square, how exactly the field of view size and shape is, if it's dense packed or loosely packed. This is all something for our feasibility study. However, these IFUs will look like, just want to make the point that there is a large expertise in building IFUs within the consortium. So the images you see to the right, the very familiar PPAC IFU or the lens array, virus IFUs, all these kind of things have been built here. So therefore, we think that we know what we can do here. Just as an alternative concept, you may, given that we are looking at a survey, want to think about going from the modular spectrographs and also having an IFU that is modular. So basically, each spectrograph has its own IFU, in that case, obviously smaller. And if you arrange it with a spacing, then you can have a dither pattern. So in that case, as you see on the top right, the spacing is 30 arc seconds and the IFU size is 30 arc seconds. Then with a 4 dither exposure, you fill your field the same way as if you would have a big field and do 4 exposures next to each other. The advantage of this alternative concept would be that it's highly modular and it allows actually for 2 things. First, a flexible deployment during your integration time, and also later, if additional funding becomes available, you can actually easily upscale the instrument. And there's a very nice example for that, where this has been done to a much more extreme, which is the virus instrument at the 10-meter Hubble telescope. They actually have 78 IFUs, and altogether we have deployed 35,000 fibers at the Hubble telescope in that way, and you see the plug plates of virus on the lower pictures. I do apologize for this bad PowerPoint Photoshop attempt here. Obviously, this is not how Gamakka will look at Calar Alto, but in a sense, it captures the simplicity of the approach that we are proposing here. So we do have modular spectrographs being placed in reality, obviously, on a kind of vibration isolated table with an enclosure. But then there is a fiber feed, hopefully with not too much additional length. Maybe we can avoid to go through the elevation chain, and then going into the Carmenes front end. If you wonder if that is too simple or cannot be done, again, I would like to just make the point that for virus, this is exactly what has been done on the Hubble telescope. So there the front end sits on top of the telescope in the prime focus. You see the plug plate on the top, and just fiber cables are basically routed along the telescope structure to the spectrographs on the sides. And these have 18 to 24 meters in length. We would think that we don't need anything longer for Gamakka. So all these things have been actually deployed over time. And in fact, that allowed the HEDEX, the Dark Energy Survey at that telescope to start 2 years ago. So they have already detected some 10,000 sources and had a first data release last year and a second one this year, while the field is still being upgraded during the survey. The spectrographs. This is actually specified by us and has been redesigned by Winlight. They are based on the modular Muse spectrographs. And these things have been already presented by Benito Moralejo in 2016 in both an SPIE paper and also at the previous Calar Alto workshop. Very basically, left is the fiber slit, then you have a slit shutter, collimator, the pH grating in the center, and then under an angle, the camera optics and the detector to the right. The rough length of everything is around 2 meters. At the moment, we do have a very wide grating inside there, covering a large wavelength range that obviously would need to be replaced. So the Gamakka bandwidth, as indicated in green, is set from 430 nanometers to 680. But the slit length, the magnification, and the F number is actually given. These spectrographs exist. In fact, 2 of them are at AIP. They are tested and they have been validated. So I'm not showing any simulated data here. This is real measured data by Benito. Shows 400 calibration, 400 spectra, continuum light, and how well they can be separated in terms of low crosstalk. This is also not a ZMAX simulation. This is measured emission line spots with a ×20 magnification, showing a very good image quality across the detector, spatially and as well in terms of wavelength. And also the detector systems do exist. They consist of E2V 4K detectors with 50 micron pixels, anti-reflective coating, custom-built detector heads, Magellan controller, and a cryo-tiger cooling system. For calibration, as said, we do not think that we need a dedicated calibration unit, but we would just do the procedure as done for PMAS PPAC and illuminate via the dome lens and the telescopes. And from the Khalifa results, we think that the wavelength resolution is quite good enough. And we have the advantage that the Gamakka spectrographs will be actually stationary, unlike PMAS. However, we can do experiments with fiber bundle and those spectrographs already at AIP, and that's also part of the feasibility study. Data reduction software. Here we can build upon the existing P3D data reduction software by Krista Sandin and also the Khalifa pipeline and Pipe 3D. Sebastian Sanchez is part of the consortium, and Krista Sandin also is available to adopt software for Gamakka. Cost estimate. We have provided these costs in the proposal. The baseline for 4 spectrographs and 2,400 fiber IFU is 2.1 million euro. And the available hardware, as you've seen with the 2 spectrographs and detector systems and cooling systems, is 900,000. So each additional channel basically is 450,000 euros. And most of the costs you see there are actually based on real quotes or actually on real orders. In terms of the feasibility and trade-off studies, we obviously foresee that we work on the IFU, modular IFU versus a monolithic one, fiber configuration, the shape, the sizes, the trade-off between crosstalk and field of view, sky subtraction fibers, yes, no, how many and where, eventually a thermal stabilization for the spectrograph, and the general trade-off between resolving power, wavelength coverage, and so on. Overall, we think that we have really a high to very high technology readiness level here. So basically all of the components are technologically demonstrated, or they are even built and physically existed and are qualified. So the risks are not that high. We talked about the stability of the fiber output during this cable movement. That's something we can test here in advance. We learned that for the Cryo Tiger, we have to replace the cooling gas to be, in terms of the fire safety compliant. And as Jakob said, there are work packages which we still have to allocate. The project planning is very much as you would foresee for such a project. It's a 6-month feasibility and trade-off study, a concept review, 1 year for a design phase and a design review, and then we are in the building and MAIT phase at the institutes first for a year, and then after a local acceptance review for, as we think, an integration phase which would happen at IAA, being close to Calar Alto, and then after acceptance there, shipment to Calar Alto. What may be different to a normal schedule is that we think that after the concept review already, we can go off and order more spectrographs, VPHs, and CCD systems, because there is no design effort needed. The design exists, and they should be identical to what is available already. So in conclusion, the Gamakka instrument concept is really based on proven and available technology from end to end with a high technology readiness level and therefore low risk. We do have almost 50% of the instrument, 2 spectrographs, 2 detector systems, and cooling system existing at AIP, and they show excellent results during their acceptance testing. Therefore, we think we can implement the whole concept on a short time scale of 3 years with a moderate budget. So if you add contingency, we're at 2.5 million euro, and with 1 million euro of AIP in kind, that's 1.5 million euros which is left. It's a highly modular concept, which means we can deploy it in phases and it can be extended later on if more budget becomes available. It's a fixed format spectrographs, no moving parts apart from shutter and the pickup element, therefore should be compatible with Calar Alto operations, and the option to switch over to Carmenes and PMS will remain with this concept. And last but not least, we think the consortium members all have a large expertise in fiber-based spectroscopy, really from the instrumentation development, the data reduction, the survey expertise and operations, and also a proven record for the scientific output. So, muchas gracias, everybody.
Okay, thank you very much, Andreas, for your presentation. Is there any question for Andreas? Yeah, one question, Andreas.
Andreas, G speaking. Actually, I have one. As an observer, I was wondering, was speaking a lot about spectrograph, but if we need to do some imaging, imagine a GRB or gravitational wave counterpart, we'll need some kind of good imager. So would the acquisition and guiding system in the spectrograph be of sufficient quality to take good and deep images maybe in various filters?
I'm really sorry. I think I only caught half of what you were saying. You were talking about the acquisition and guiding system. That's what I understood. That is something which would sit in the front ring to make sure that our image stays on the IFU. Was this your question?
My question is only to know if the optical quality of the auto guider and acquisition camera was good enough to take deep images in case we need to take images in case of GRB or gravitational wave counterpart, for example.
In terms of that, we obviously would foresee an acquisition and guiding system, which is not a auto or TV camera. It would be a technical camera, a technical CCD sitting in the front ring.
My question was actually just related a bit to the acquisition camera of PMAS. It's my favorite instrument, but I have to complain a bit about the quality of the PMAS acquisition camera, which is probably not good enough to take good deep images in case we need to do so.
I mean, the PMAS acquisition and guiding camera, as you know, is a scientifically nitrogen-cooled camera. I do not think that we will do anything better with the technical A&G camera for Gamakka.
Yeah, that's the point. It's delicate. Thanks anyway. Thanks a lot.
Is there any other further question for Andreas? No? Okay, so thanks to all the speakers of this session, and now it's time for coffee break, and we'll be back at 11. Okay? Thank you very much.
Thanks very much, and I hope you're all happy and healthy very soon again.
Hola, Armando, ¿qué pasa? Es que...
Hello?
Hi.
Hi, Vicent. Okay, first of all, let me, all of you, give me my welcome to the IAA, although this time it has to be virtually. I would have enjoyed to welcome you all at our institute, but since you know that this workshop is especially important for our institute as reference institute for the Calar Alto Observatory. But okay, the issues with the COVID has made it impossible. Then we have, I think it has been a whole success, the whole meeting, just do it interactively. Just now we go into the authority session. The first thing I have to do is just to excuse the presence of Rafael Rodrigo, Secretario General de Política Científica y Tecnológica from the Spanish Ministry of Science and Innovation. He couldn't join the meeting. And also from Pablo Cortés, he is the General Research Director of the Regional Government of the Junta Andalucía. He also cannot make it. But we have the opportunity to listen the presentations by Vicent Martinez, coordinator of the Spanish Astronomy Infrastructure Network, the so-called RIA, Red Infraestructura de Astronomía. Hi, Vicent, good morning.
Hello, good morning.
And from Jesus Marco, also the Vice President of Science and Technology from the Spanish CSIC, from the Spanish National Research Council. I think Jesus should be around. Hi, Jesus. I don't know whether you can listen to me. Not still. Okay, then we are going to start with presentation by Vicent Martinez.
Sorry, I was closing the window. It was too noisy. It's okay for me?
Yeah, we can listen to you perfectly.
I'm not going to share any PowerPoint presentation. I wanted just to, although I was already connected a long time yesterday and I have been following many of the talks, I think that the first I want to say is to congratulate the organizers, just to act so quickly in these conditions of the coronavirus outbreak. It's clear that you make the right decision in the right moment. And this is something that is very difficult to say now, because we are seeing that many decisions are taken and sometimes they are not in the right moment, but you did it. And of course, the idea of the workshops was really timely, as Jesus Aceituno was explaining yesterday in all the process that started nearly 1 year ago, or a bit more. The process of finding the new instrumentation for the Calar Alto Observatory has been following exactly the path that it was established a few years ago by the network, the RIA, the Network of Astronomical Infrastructures in Spain. And I like to say that it's probably the best organization doing this. I mean, because it's in the page that every infrastructure has to follow when they have to face what kind of instruments have to and what kind of science have to be done in the future. It's clearly stated in some of the documents that everybody knows and are in the network website. And but you know, not all the infrastructures follow as well as the Calar Alto Observatory and the Instituto de Astrofísica de Andalucía is doing. It's important also to say that I am quite happy with the structure that the observatory has dealt with the last 2-3 years. As you everybody knows that when the German part was living in some way, that was a moment of crisis, and but I think that you solved it in a way that was absolutely perfect, and I guess that it is also a way that should be followed by other institutions in the network. Then going back to the topic of the meeting, I have been following some of the talks. I think that in this moment to have a authority session at nearly to the end of the talk, it's something that is not usual, but it has also some advantages because you know more or less the results. And I want to congratulate that certainly Calar Alto is a quite active place with many projects ongoing, with a lot of discussion of what should be the best. I think that the fact that the meeting has been followed typically by 50 persons proves that people were quite interested. It was a pity not to have the opportunity to meet together, but we are also learning that probably this will happen more in the future. In all sciences, this also will help not only to avoid some problems that we have now with the coronavirus, but probably with other problems that the planet has. And we are learning. We lose our contact, but certainly in this moment it was not possible. In any case, I want to say that when we start this process, we have very beautiful instruments at that moment, and we have a very interesting scientific discussion in the committee that had to do the selection. The selection of Luca was certainly based on the solid scientific grounds, but the time has proved that it was not probably the best because of the reasons that have been very well explained in some of the talks, particularly in Jesus Aceituno talk yesterday. And now we are facing the future, and you have presented many interesting approaches, and also a process that now starts with the new applications and evaluation of these applications in the same way that it was done before. And I am quite happy also as the coordinator of the network to take part in this evaluation and to put my knowledge and also the knowledge of other infrastructures, because part of our work, in particular in the network, is to find out what is the real position of this particular infrastructure in the context of the others, and taking into account how is the synergy that for the best astronomical instrumentation for the whole Spanish and international community we have to decide. This is a process that started now. I will also look in more detail some of the talks that I could not follow directly, but now are already in the web repository at the network web page. And what I will say, just for finishing, is that congratulations for keeping the meeting alive in this way, for solving all the technical problems, for teaching to the community that big problems needs that intelligent people try to find good solutions, and you did it. And we will be in touch for during the next weeks and months to follow this meeting, that it was really timely and proves that everything will have to continue for Calar Alto. It's clearly the main astronomical infrastructure in the continental Europe, and this also gives you a strong responsibility, in the sense that all the instruments have a beautiful future, and the results have been impressive. We can talk about Khalifa, Carmenes, Alhambra. The idea of having Calar Alto as an infrastructure that is mostly devoted, but not only, but mostly devoted to legacy projects, and the ability to choose these projects is the point that we have to take always into account in the context of the astronomical science in the world, in Spain, and taking into account the big instruments that you have already working for a long time, and the big science that you have already done with the numbers that already have been explained of publications in high-impact journals, and also discoveries that have been really impressed the whole community. And this is my words is just to encourage this page, and of course I will help in what I can do, and the network will be always very proud of one of its infrastructures, Calar Alto Observatory, and will help in. And in particular, I want to say, and this is the end of my interview, that in the recently published Estudio de Prospectiva, that many of you will receive in the following days. It was presented in the last presential meeting in Barcelona a month ago. We have not sent it to already. We have the books or in boxes, but following a suggestion by Isabel Vázquez, we have to claim for the numbers, the legal numbers. It's a very nice publication. So we rush it. We publish it very quickly to have it in paper in Barcelona. But at this point, we need what in Spanish is called depósito legal and ISBN number in order that it will be disseminated along the institutes and the people who wants to have its own version in paper will just claim it and it will be sent directly. But in this document, you can read in many places the role of Calar Alto, and in particular, I wanted just to say that it was the last place where the last coordinator of RIA, Jordi Torra, did observations. It was clear, and we can say that if he has a favorite infrastructure, it was Calar Alto, without any doubt. It was the one that he has more in his heart, and this was mainly the reason that he spent a few weeks the year before he died in Calar Alto doing observations, and it was one of the things that many of the people who talk in the session that we were devoted to him well recorded. Okay, that means that Calar Alto is something that I have to take as much as important as Jordi did, and I try to follow his advice, and I will do it. Thank you very much.
Thanks a lot. I want to say, yes, that here, as representing Calar Alto also, we have always felt the support of the RIA for the infrastructure, and thanks a lot for that. Okay. In fact, I still, just remembering, as you have just now done, in this workshop in Barcelona, the observer that was with Jordi Torra in the last night, in the last observing night, he was mentioning, in fact, that he was happy. No? He was at that time very happy about being able to be observing still at that time, and that's a very good thing. Okay, thanks, Vicente. Then we go to next speaker, that is Jesus Marco. This is the Vice President of Science and Technology from CSIC, from the National Research Council. Jesus, are you around? Is train Jesus? Let me check that. Jesus, try to get in contact with him. ¿Le llamo?
He's getting some trouble.
Yeah.
Okay. ¿Me oís bien, verdad?
Sí, okay, here we are again.
Okay.
Yes, sorry for the problems with the connections. As mentioned, we have the second speaker today, that is Jesus Marco. He's the Vice President of Science and Technology from the Spanish National Research Council. Good morning, Jesus.
Good morning, Anton. Good morning, Jesus. So, it's my turn now?
Yeah, you can start
okay.
you want.
Okay. Thanks. Well, I will say only a few words. Just first of all, to thank you for all this effort that is ongoing. I have been following the slides and only partially some of the presentations, and I think the efforts are well directed. I would like to emphasize that CSIC, the National Research Council in Spain, is supporting very much this effort, and we hope that the session concludes with new ideas. I have seen already improvements along the development of these 2 days, and that of course now the hard work has to be done by the advisory board that will consider carefully these proposals. I have been also positively impressed by the ideas where also new instrumentation will take place. Of course, also a connection with parallel observations, also the further development of successful instruments. All this is very promising. And my message today is just that you keep the good work. And thanks all of you, and in particular Jesus and also Anchong for organizing this meeting and going forward with all these proposals and organization. I don't know if you have specific questions to me or otherwise that's it.
Not from my side. I don't know whether there is any question coming via Zoom or no. It's not the case.
Okay.
Jesus, then, thanks a lot for your participation.
Thanks. And keep the good work. Bye.
Bye.
I will keep the connection open.
Okay, good.
Just to follow what goes on.
Very good. Okay, yes, then to finish with this authority session, let me mention that I am very happy with the presentations and the quality of the science that has been proposed, and as mentioned by Jesus, with clear improvements over the proposals that were already submitted. From the point of view of our institute, the IAA, it is important that there is a strong presence of both our scientists and engineers in many of the proposals that have been shown during these days. The decision won't be easy for the advisory board, and I think this is by itself the first great conclusion of this meeting. And I am sure also that it will secure a powerful future for the Calar Alto Observatory. Only doing the best science, Calar Alto has a clear future. Thanks a lot for all of you, and I think at 11:30 we will restart with the scientific sessions. Okay, bye-bye.
Bye-bye. Thank you.
Hello, everybody. So we are starting again with the last session, the two pending talks. First one by Martin Roth. Are you there, Martin? Martin?
Yes, I am.
Okay, so you can start. Go ahead when you want.
So, hello everybody. Thank you very much, first of all, for inviting me to give a talk here. I told Gilles the other day that my heart was bleeding of not physically being there, but congratulations of having managed on short notice to set up this all by Zoom and YouTube. So this is quite a bit of infrastructure set up in no time. If you allow me just one word to connect to the previous session, where it was mentioned that Germany had pulled out of Calar Alto. I want to confess that I was very unhappy when this happened, but please be reassured that there are many groups in Germany who love Calar Alto, and I personally feel very much attached to Calar Alto, to the IAA in Granada and all the other institutes in Spain, given the connections that we have established. So this workshop, I think, gives evidence that after a very difficult period of time, as we all know, Calar Alto is on a route towards future, and this is very reassuring. I'm very happy about that. And the second thing is, it is infrastructure, yes, but I think in essence, it's all about the people. And I just want to say that Calar Alto has a fantastic, very motivated, competent staff and a director who has steered the observatory through very difficult periods of time. So thank you for your dedication and your support. It's always a great pleasure to be on Calar Alto. Now, having said this, let me switch to the presentation, which is obviously geared very much towards IFUs, as the title says. I've realized over the past 2 days that we have, amongst many other interesting capabilities of Calar Alto, two big legacy capabilities developed over time, one of which would be Carmenes and exoplanet research, and the other one would be IFUs. And I was very pleased to see that there have been plenty of proposals, either for surveys and or instruments and surveys. So I hope I can make a contribution here, referring to resolved stellar populations, where we think we have now achieved a breakthrough, and this is the topic of this talk. There are many people involved in this effort, also linked to another instrument, the Muse instrument. I will not go into many details, but just tell you by reference to some statistical data that I feel that we indeed can claim that Calar Alto has developed IFU legacy. You probably would agree. But if you look, for example, into the statistics of publications resulting from VLT instruments published by ESO earlier this year, from 1999 to 2019, and then compare this with just the PMAS publication record between 2003 and 2019, according to what is registered on the Calar Alto webpage, then you can say, well, we're not doing so bad. But if you look precisely into last year, there are only 3 instruments at ESO VLT, like UVIS, Muse, and Extutor, who have more publications recorded in 2019 than PMAS-related work. So from that point of view, since PMAS is coming of age, I think the proposals that were made yesterday and today are very encouraging to build on that legacy, and are very much encouraged to do so. So let me now come to what I think is a future trend. And you may be surprised if I refer to the ELT, which is 2 classes higher, if you like, than 3 to 4 meter class telescopes. In the science case document for the ELT, then called EELT, you find a paragraph about resolved stellar populations. And if you allow me to read this, here, quote, nearby giant galaxies have remained diffuse nebulae that cannot be resolved into individual stars. The unique angular resolution of the EELT will revolutionize this field by allowing us to observe individual stars in galaxies out to distances of tens of millions of light years. By the way, please remember the little image on the lower left, Galaxy NGC 300, we'll come to that. Now you may ask the question why I'm quoting the flagship project of European astronomy when we speak about the future of Alto. I will try to convince you that what was actually introduced by Armando yesterday and by Jakob today with regards to stellar work, we do have all the ingredients at hand, and I will try to actually show you some arguments why the ideas actually will work, in my opinion. So first thing is already mentioned by Jakob, a technical thing. Pampelmuse, the Potsdam Advanced Multi-PSF Extraction Algorithm for MUSE, unspeakable, the software tool developed by Sebastian Kamann in his thesis here at AIP, for actually what I would like, and I often quote this as the analog, to be like crowded field stellar photometry, CCD photometry, that was introduced in the seminal paper 1987 by Peter Stetson. By the way, citations more than 4,500 as of February this year, to be further developed into what we call crowded field 3D spectroscopy. So the transformation from just images to data cubes with PSF fitting techniques. So this is Sebastian Kamann's work, and you may wish to compare the number of citations in ADS, which is not that large at present, but if you also from ADS consult the history, you will see there's a peak rising in 2019, and I will claim that we are actually at the verge of a breakthrough with techniques addressing partially resolved stellar populations or fully resolved stellar populations in more nearby galaxies or clusters. And here's an example of what was accomplished in pioneering work at Calar Alto. I have no chance to go into any details, but I just can tell you that kinematics was obtained from stars, individual stars resolved in 3 globular clusters that you can depicted here and published by Sebastian in 2014. And this leading actually to a breakthrough at the VLT with work using the MUSE instrument, which has a much larger field of view. And I just can tell you this graph is quite impressive even to me. It shows the content of what yielded more than 12,000 spectra, just with a snapshot series of 1-minute exposure of a 5x5 arc-minute field of view. And to conclude this, just to show you the signal to noise color-coded in the CMD for that cluster NGC 6397, where you get well 5 magnitudes below the turnoff and have a signal to noise around 100 on the RGB and on the horizontal branch. This has become an industry, and I could give a full talk about results of a GTO program on globular clusters, which involves kinematics, chemistry, finding emission line objects, etc., even black holes, binary studies. We have like 11 papers from that GTO program, and a recent paper by Sebastian Kamann again is very special in my mind because he has demonstrated with an intermediate age cluster in the LMC that it is possible with low resolution of the one that MUSE presents to even resolve lines to measure rotation. So it was capable of resolving the main sequence of that cluster. Please read that paper, it's quite amazing. Now, when I claim that we are at the verge of a breakthrough, let me underpin this with a few examples. And here I have a couple of papers. The first one being on 30 Dorados, published by Norberto Castro in 2018. He's now working at Potsdam in our team, where he obtained several pointings in that dense region with a total of more than 2,000 spectra, of which he was able to derive 270 radio velocities. for massive stars. So this is already connecting to Jakob's presentation, but also in part with regards to OB stars, as mentioned for Tarsis. And also gas diagnostics was provided for this field. The second paper is in preparation. And then similar topic, a paper published by Seidel et al. On Westerlund 2, where they had a couple of shallow pointings and 3D pointings of 1 hour each, yielding in a total of 72 spectra and associated spectral type classifications and radial velocities. I am going quickly through all of these examples just to give you a flavor of what has been accomplished in the last few years. Moving further out to local group galaxies, here at a distance of 1.6 megaparsec Leo P, Chris Evans and collaborators have published data with 1D pointing in that galaxy with almost 7 hours, from which they obtained 341 spectra, of which the large majority remained unclassified, but I highlight AGB stars they found along with the massive stars that are of primary interest. And if you look into this narrowband image in H alpha, this demonstrates the superb sensitivity of IFUs to find emission, where you see very nice supernova shells. Now, a bit closer to home, this is a beautiful paper by Maite Alfaro Coelho at MPIA, where in her thesis work, she studied the cluster of the Sagittarius dwarf galaxy with 4 pointings of Muse, from which she obtained 55,000 spectra, out of which 6,600 yielded an analysis, a good enough signal to noise, with ULIS to find actually 3 stellar populations with different metallicities and ages. It's a fantastic work to show that indeed what we are planning also for Gamaka is going to be possible. Then even further out, here's the galaxy that you perhaps remember from the ELT document, NGC 300. There is a project led by Anna McLeod, providing a mosaic of 5 by 7 pointings, relatively shallow, out of which the first paper was published last year, where they investigated a couple of massive stars in that region. And I myself have been engaged in this galaxy since already at the previous workshop in 2016. I presented examples from this work. I just refer you to the pilot study paper. This is still work in progress with even improved image quality using the AO mode, but I can tell you that we reliably now can address very crowded fields with this kind of technique. Now, I want to conclude my presentation with showing you examples that are more closer to home, and actually, if we regard M31 as home, almost at exactly the same distance. This is the Dwarf Galaxy Ic 1613, observed with Muse in a program by Giuseppina Battaglia. And I'm involved in the analysis of 3 fields that were obtained there, indicated here. And here you can see the reconstructed broadband images from the 3 data cubes. And if you focus on field 2 in the middle, I can show you a few examples. Here's a blue star in that frame. And if you look at the spectrum, an analysis with the ULIS code and the extended MILIS library yields, well, as expected, a blue star, subgiant of class B3, and a velocity of minus 231 plus minus 25 kilometers. We'll argue that the error estimate is actually an overestimate, but anyway, the systemic velocity is minus 235, so this is fitting into the picture. Another star, this yellow star, blended a little bit with the blue star on the bottom. It's actually a K star, K3 subgiant. Also the velocity indicated, and you see very strong calcium triplet, magnesium, sodium, iron, so it's all there. And this would be with a signal to noise of 30, suitable for measuring metallicity. This is work in progress. If you go to fainter stars, like the one here, which has a signal to noise of 7, you still get a good signal to noise, good enough to a velocity, which also makes sense, where the error is getting larger, but you probably will see that still you see the calcium triplet, the Balmer lines, and the entire set of lines that disappear in the signal, the noise on the signal, make it possible to obtain, even in the event of low signal to noise, a reliable velocity. As even in this case of signal to noise 5, where you have a late G star, as you can see, where marginally can make out the major strongest absorption lines. Here's again a brighter star, yellowish. This is a wonderful example for carbon star, where you can actually pinpoint the velocity to less than 1 kilometer per second. And the orange curve is actually fit to an Exeter library template, almost indistinguishable from the measured spectrum. And then there's a very red point source here. Now, this is actually a galaxy of redshift 1. So you can easily, and this is not possible with photometry easily, distinguish background objects which appear as point sources. Or this other star just on the corner, which happens to be an Dwarf, or a main sequence star, which cannot possibly be seen at the distance of IC 1613. And if you look at the velocity, it's also not fitting. So again, you see even foreground objects you can easily sort out. A big advantage of spectroscopy. Now, I can tell you that I am not trusting the velocity areas that Ulysses is yielding. Salvatore Taibi, in his thesis project, is actually using the RV SpecFit tool and is yielding fantastic results as to the velocity field that you can actually use and just merely face on galaxy to even determine a rotation curve, the velocity dispersion. Look forward to the paper, which is in preparation. I'm really convinced that this is a great progress forward. And just to support Jakob's statement that even in the event of low signal to noise, you can derive velocities. Here's the result of a simulation, Monte Carlo, where in different segments of signal to noise from left to right, 30, 20, and so forth, down to signal to noise of 1, you can see that the distribution around 0, which should be the target velocity, is behaving very well. So that we can trust that even for noisy spectra, that as we are not having Muse available, but we are planning to use build a new instrument, will be capable of achieving at the 3.5 meter. And finally, here is a color magnitude diagram from the FAT survey paper, Dark Continental 2012, where you see that down to magnitude 22, which is the target that we have for Gamakka, we would actually get the tip of the red branch, the AGP stars, and also the main sequence hot stars, red supergiants. So quite a bit to explore, kinematics, and for the brightest stars, even metallicities. So let me finish up with the conclusions. I hope you have accepted that crowded field IFU spectroscopy is an established tool. We have already demonstrated applications from the Milky Way, globular clusters, and so on to nearby galaxies, even beyond the local group, that we are capable of measuring radial velocities thanks to a large free spectral range, even at low signal to noise, and that for the higher signal to noise cases, we can hope to obtain metallicities. And I hope that the last slide has convinced you in scaling the IC 1613 to the 3.5 meter telescope demonstrates the feasibility of projects like Gamakka and TASIS as stellar science cases. If you want to look into more detail in the quoted work, please consult the review that is listed above, and this is then the end of my presentation. Thanks very much for attending.
Thank you very much, Martin. Is there any question for Martin? Questions? Okay, so we don't have questions. So we move on to the last talk of this workshop. Thank you very much again, Martin. So next speaker is Jesus Gallego. Are you there, Jesus? Jesus?
Yes, this is Jesus speaking.
Okay. So once Martin switch off the sharing window. Yes, we can hear you. You can share your window, Jesus. Okay. Is this? I think no. This is Martin. Can you please switch off sharing windows? Because I think. Okay. Thank you very much. Jesus.
Yes.
Can you share your window, your screen? Sorry.
On my way.
Yeah. Okay.
Do you see my screen?
No, we don't. Now, yes. Now, yeah. We can see your screen. So you can start when you want. Thank you, Jesus.
Okay, good morning, everybody. This is Jesus Gallego speaking from Madrid. First of all, thank you very much to the organizing committees for organizing the meeting under such difficult conditions. My talk is to present the current capabilities of the Universidad Complutense de Madrid Instrumentation Group. And we have been always very close to Calar Alto, and this is very special for us. 20 years ago, we were just a group of university teachers and researchers in extragalactic astrophysics. We used to go to Calar Alto for observing runs, and we have been there enjoying both science and friendship with the Calar Alto team. Today, we are a similar group, but we a great capacity and experience in the development of complex instrumentation projects, in collaboration with both academic and private companies parties. So my talk will concentrate on our lab facilities, our laboratory, our expertise in the development of small instruments for light pollution research, data reduction pipelines, including GTC instruments as Mira and Megara. Our major success, which is the design, development, and successful delivery of the Megara Spectrograph for ground telescopic areas. I will mention our expertise commissioning complex instruments as Megara and Emir. And I will also talk a little bit about our plans for the future, mentioning our contribution to the Mosaic Spectrograph for the ELT in close collaboration with the Instituto de Astrofísica Andalucía. Finally, I will have a final slide for lessons learned. So let me start mentioning the backbone of our instrumental activity, which is our Laboratorio de Instrumentación Científica, what we call LICA. It is a top-level facility at the Facultad de Físicas building, where we have already carried out several activities related with complex instrumentation, as you can see in the different major successes are the Imf and Megara data reduction pipelines. All these software is Python-based. It's always fine-tuned for the instrument. It includes automated processes, and it follows a Creative Commons license. I just show here some examples of the capabilities of these data reduction pipelines. We are still supporting these pipelines already available for the community. And as summary, I would mention that well, the bottom line is that the reduction pipelines, both the Emir and the Megara ones, are the official pipelines approved by Grantecan, offered to the GTC community. Our major success, no doubt about it, is the conception, design, and development of the IFU multi-object spectrograph Megara for the Gran Telescopio Canarias. It was a long and winding adventure, I would say. It started in 2010, and we finally delivered the instrument in 2017. The instrument is a complex one, including optic fibers, two different elements, one in one of on the folded cast focus of the telescope, what you see there on the left, and it also includes in the Nasmith platform an optical bench supporting the spectrograph of the instrument, as you can see there on the right. We also develop the expertise for the work for the control work package, collaborating with our colleagues at the IAA again. We have now a very close links and connections with the IAA. And well, despite it was a complex instrument, it was many years, we finally were able to deliver the instrument in time. Just to show the complexity, I am showing down on the right and on a small movie, a short movie with the positioners of the instrument for the multi-object spectrograph observing mode. I don't know if you can appreciate that the different elements are moving to point different single targets. The multiplexing of the instrument is close to 100 in the multi-object spectroscopy observing mode. And of course, the instrument is already available at GTC, is already producing nice science. I don't want to focus on the obvious power of the IFU spectroscopy, but it is, I can say that it is obvious that there is a lot of future in this observing mode. I'm going to show a short movie on the right. It covers just 12 kilometers per second per channel, and this is a synthetic image of the NGC 604 star forming region at the Imf 33 spiral galaxy, close to the Milky Way. And we can see how the profile of the emission line is shown during the movie. The participation in the international consortium for the development of Emir and Megara gave us the opportunity of building a very nice expertise, not just designing and developing the instruments, but something which is crucial, which is the commissioning of the instrument. We have spent a lot of time during the last 3 years at the GTC telescope, just commissioning the two instruments. So as a summary, I would mention that the main goal was completed, Megara was completed. It was done on time, which is crucial. We delivered the instrument to GTC in May 2017, and it was done in fully compliance with their requirements. Just to show you that we deliver science as soon as possible, 5 papers just from the commissioning and the guaranteed time only have been already delivered. And I'm pretty sure that our expertise in Megara and Mir provides a huge potential for scientific follow-ups with other Spanish facilities, including Calar Alto. What is the future for our team? Well, we are already involved in a long-term project, which is going to be the baseline of our activities in, I guess, the following 10 years. And again, in a very close scientific and technical collaboration with the Instituto de Astrofísica Andalucía, we are contributing, we are the Spanish contribution to the MOSAIC. MOSAIC is the multi-object spectrograph for the European, for extremely large telescope, the ISO telescope that hopefully will be delivered to Chile in 2000, will be finished in 2025. I have to mention that this is a huge European collaboration, it's a huge consortium, and I have to mention that this is also a long-term project. The main workload will not arrive to our institution before 2024, and we are planning to deliver the instrument no before 2029. The UCM and IAA contribution to MOSAIC focused on the calibration work package and important contributions to the control of the instrument. The instrument has a lot of contributions from different institutions all around the country. Simultaneously, our group is quite active and is trying always to bring new resources, new projects to the team, to keep the team alive, to keep the team active. I just show a list of different initiatives. I don't want to go into the details, but this is just to show you that we are quite active and we are always looking to bring new resources from different financing agencies and from different financing sources to keep just a baseline of activity with no interruptions. So this is my final slide to summarize. I just wanted to emphasize that UCM and collaborators in the TAR6 project, including several Andalusian institutions, what we can offer, or the best we can offer, is both reliability and innovation. Our lab facilities are ready. Our know-how, team, and structure, it is just the heritage from Megara, is ready, and is ready now. Now is the right moment, because perhaps after 3 years could be gone. Please keep that in mind. Our expertise in data reaction pipeline, exposure time calculators, associated software is ready. Our experience, our expertise in commissioning techniques is also ready. And what is more important, we are in an excellent moment. We have keeping an excellent timing with other ongoing projects. I mean, there is no conflict, for example, with the development of MOSAIC, which is because that is a much longer project. I just would like to emphasize my two last sentences. Sorry, TAR6 means technological return on investment for Spanish institutions and companies, including the patents level. And moreover, it would be a Spanish-led state-of-the-art science and technology for Calar Alto in the extremely large telescopes here. So we are ready for TAR6. Thank you very much.
Thank you very much, Jesus, for your talk. Is there any question for Jesus? There are no questions, so thank you very much, Jesus. So this is the last talk of the workshop, and we are proceeding with the official closing of the workshop. From my point of view, I would like just to thank all of you for attending the workshop, for being so patient despite the inconveniences technological reasons because of the current situation. I also would like to thank the Instituto de Astrofísica de Andalucía for hosting the workshop and for helping in the organization. Also to the committees, the organizing committees, the scientific organizing committee and the local organizing committee. All of them have worked a lot and they made this possible. And that's all from my side. I think that Jesus has something to say before closing.
Yes, well, I'm going to be brief because this is just the closing act of this workshop. And but I just would like to highlight the success of this workshop in many aspects, not only in the number of proposals that show a very clear support from the scientific community to the continuation of high quality science at Alto, but also because all the technical issues that we have fixed, just in the last minute we took a decision. And to be honest, I was very concerned about the success of the realization of this workshop. But now that we are just closing, I think that maybe this is going to be something to reconsider for the future events, because it's absolutely feasible just to do this kind of workshops. As Jorge mentioned, I want to extend as well a huge thanks to all the attenders, to the SOC, to the log of the workshop. You have made possible this workshop, but also especially to RIA for supporting this workshop, and also very, very special for IAA for hosting us here and giving always their support to the continuation of Alto. Now we have a very hard work in the future because the quality of the proposals are very competitive and they are placed at a very high level. And the Scientific Advisory Committee has a very strong work because it's going to be difficult to select the best ones. I just want to note that next week we are going to, as I told in my talk, we're going to make the official standard call for the proposals. As a reminder, we are going to continue with offering the 20% of open time to the community. But for the rest, we are going just to take a decision, or we are going to do all the best to take the decision to start immediately with the legacy programs. But due to the current situation, maybe this could be delayed. So we propose to all the community as well just to submit the proposals, not in that case legacies, but short term. They can be considered, for instance, at pilot proposals. But just submit also for the standard calls because your proposals will be always welcome. And we are going to provide the different links of the different sessions through different web pages, in Alto web page, in the RIA page, and probably we will send as well an email to the SEA, the mail distribution list. And again, thanks so much. Take care, and we will continue working together. Thanks so much.